Let me describe a scenario for you. You're developing a code, so you install all the basic software development tools you might need. Git, compilers, a Python interpreter, a text editor, maybe some sophisticated IDE. Then your code has various library dependencies, so you go ahead and install the latest versions of those. And after some hours or days, you've got everything set up the way you like it, and you throw yourself into your development work for a while. Then, at some point, you decide you need to install a new software package. It might be something totally different from the development work that you were doing before. And as you're installing this new software package, you find out through trial and error that it's not compatible with the latest versions of the libraries that you had previously installed in your software development work. So you roll those back. You get that new software package working, and then when you return back to your development work, you find out that doesn't compile anymore because you actually do need the latest versions of those libraries. So now you spend more hours trying to get your system environment back to a state in which you can do your development work again. Then maybe sometime later you get a new computer and it doesn't have all of these nice development tools you installed. So you have to go through this entire process again, and you spend another few days being unproductive because you're just trying to get your development environment set up properly. Then maybe sometime later you start working with a colleague on development of this software project. And you end up having to spend hours or days helping them get their environment set up so that it runs properly. And maybe you encounter new difficulties that you hadn't before. Things that worked on your machine don't work on your colleague's machine. And you may end up scratching your head and struggling for a prolonged period of time trying to figure out, why does it work in my environment but not in my colleague's environment? These are all the sorts of problems that container native development is meant to solve. And this is the first video in a series from the MolSSI that are going to introduce you to best practices in modern software development. Now, the challenges that I've just described arise from the fact that computational environments are complicated and they tend to get messy. And when you make changes to one, it can be very difficult to anticipate what sort of unintended side effects those changes might have and whether you might be breaking something. And modern solutions to these problems tend to lean on containerization technology. And what this allows us to do is to create self-contained, isolated computational environments that are well-defined, that are shareable, and that often will be custom designed to fulfill one particular purpose. Now, what containerization technology allows us to do is to create a coherent package that includes one or more applications, plus any library dependencies they have, whatever else they need in order to be able to run, plus even things like our basic operating system's core utilities. All of this stuff we can take together, package into something called an image. So all of this stuff taken together, we could form into an image, and an image is something that can be shared with colleagues, it can be reused, it can be uploaded to the internet, it can be downloaded by other people, and it represents everything you need in order to be able to run an application, including its full environment. And what you can do is you can take this image and you can use it to launch what are called containers. So this image could launch a container, let's call it container 1. And that container is running the complete isolated environment that you've defined in this image. It is almost as though you have a separate isolated computer that is running independent from anything else that's happening on your computer. It just happens to be executing on the same hardware. But then it doesn't just stop there, because in addition to launching a container, you might launch multiple containers corresponding to a single image. So an image really just defines how it is that you can launch these things that are called containers. And the containers that are what are actually running your application and any dependencies it might have. This is a little bit like how when you have an executable on your computer, that executable is just storing instructions. It's just data on your hard drive. It's not actually executing anything until you double click it or otherwise launch it. And at that point, from the executable, you launch a process, and that process actually runs the code. That's a little bit like the distinction between an image and a container. And in like manner, if you have an executable, you can launch multiple instances of that executable. You can have multiple processes that are running the same executable, the same code. And that's kind of what we have here. Now, where this starts to get really powerful is the fact that you can have multiple different images. So we could have this image, but then we could also have some image that we call image 2. And this image might package a different application than the one that we had in our first image. Let's call that image 1. And then you could have as many other images as you like. You could launch containers of any or all of these simultaneously. And each of these containers are going to be totally isolated from one another. They don't see anything that the other containers are doing. If you change one of your images and launch a new container corresponding to that image, you haven't in any way affected the other images or the other containers. They're just going to keep running exactly like they were before. So you don't run into these problems where you could potentially wreck your environment so that stuff that was working before isn't working anymore. You're only going to affect whatever image you're actually actively modifying. Now, in the context of development work, what we can do is we can create a nice isolated environment that contains all of the stuff we need in order to be able to develop code. And we can package that up in a reusable way so that there's no danger that we're going to accidentally modify our environment in such a way that we can't do development anymore. Now, the big name in containerization right now is Docker. And I like Docker. I use Docker. But there are some downsides to Docker that we should probably address. And one of those is the fact that certain components of Docker, certain tools within the Docker ecosystem, are not open source. And if you're a commercial company, you're going to have to pay for access to those tools. And this means that there are certain professional contexts in which usage of Docker is frowned upon or prohibited. Also, there are certain security issues associated with Docker. In particular, by default, running a Docker container means effectively granting sudo access. And that's not going to be permitted on shared systems like high-performance computing clusters. So again, there are certain contexts in which using Docker is going to be frowned upon or prohibited. And this is where Podman comes in. So Podman is meant to be a drop-in replacement for Docker. It works almost exactly the same way as far as the user interface is concerned. The same commands that work with Docker are going to work with Podman. The only real difference being that you're going to change the word Docker in those commands to the word Podman. The files used by and produced by Podman are going to be essentially the same as those used by and produced by Docker. So Docker containers are going to be compatible with Podman containers and vice versa. They're the same format under the hood. The key benefit to Podman is that it is open source, and also the security vulnerabilities that you incur when you use Docker are not going to be present when you use Podman. Podman does not by default require root access to your machine. And so Podman you can actually run on things like HPC systems. Now, to use Podman, you're going to want to go to the Podman website, click on Get Started, Installation Instructions, and here we've got instructions for whatever operating system you might be running on, whether it's Mac, Windows, or Linux. And of course, this process is going to be different depending on which of those you're running on, so just follow the appropriate instructions for your operating system, and then we can continue on to the next bit of the video. Now that we've got Podman installed, let's go ahead and try and build an image and run a container. So what we'll need in order to do this is a file called container file. So I'm just inside of a directory on my machine. I'm just going to create a new document, and we're going to call this container file. Capital C, no space, and no extension. So if, for example, you're on Windows and it tried to add a .txt extension or something like that to the end, just make sure you get rid of that. The full name is container file. There is no extension here. And this is going to be the file that is going to tell Podman how we want it to construct this new image that we're going to build. If we were using Docker instead of Podman, we would call this a Docker file, and otherwise it would work the same way. And so we can open this with some text editor. It really doesn't matter what you use. And again, this is going to be the instructions for how to build the image. Now, every image that we're going to build is going to start with some base image. And the way we specify that base image is we say from in all caps. So this is going to be at the very start of our container file, at the very start of really any container file. From, and then the name of the base image we're going to use. And let's use an Ubuntu base image, which means that everything that we're going to do in this image, it's going to operate as though we were running an Ubuntu operating system, whether we're using that distribution of Linux or not, whether we're using any distribution of Linux or not. And then typically we would want to put colon and then the name of the version of Ubuntu we want to be running. That might be 22.04, for example. In our case, we'll say latest, and what that's going to do is tell Podman just get the latest version of Ubuntu. Now we can save that, and that's all we need to do. Normally, we would add additional lines here that are going to explain how we're going to build on this base image to construct a more elaborate environment. But this is good for us for now, so save it. Now what I'm going to want to do is open up a terminal in this directory, and on my machine I can just right-click and say open this directory in a terminal. And because I'm on Linux, I can type ls, and that's the command that just says list all of the files in this directory, and you can see I'm in the same directory where our container file is. Now if you're on Windows, these commands might be a little bit different. You can click Start, type CMD to open a command terminal, and then you can navigate to this directory. Whatever it is you have to do to get a terminal open to this location, just go ahead and do that now. And then something else I'm going to do is I'm just going to show you that because I've used this particular computer to do some development work before, I've installed Git. Now, you may or may not have installed Git before, so this command may or may not work the same way for you, but I'm going to type git -- version, and that's just going to print for me the version of Git that I happen to have installed on this computer. That's just going to be a useful thing for us to know in the future. We'll refer back to that later. But the really important part is, at this point, we want to build our actual image. And to do that, we can type podman build. So at this point, all of the commands I'm going to show you are going to work the same way regardless of your operating system. So we type podman build, and then we want to say -t to give a name or a tag to this image we're going to build. And for that tag, we can basically choose whatever we want. I'm just going to call this my image. And that allows us then to refer to this image in future commands. And finally, we're going to want to provide Podman with the location where it can find the container file that describes how to build this image. And that image is in the same directory, so we can indicate that simply by putting a period there. So we can try building that, and you can see there it goes. It just built our container for us. It built our image. Now what we want to do is try and run this. So what we can do is we can say Podman RUN. And then there's a few options we're going to want here. So one that I would suggest you most always are going to want to use, unless you've got a good reason to do otherwise, is --rm. And what this is going to do is just ensure that once we're finished using the container, once we've exited out of it, the container is going to be deleted. Otherwise, you can end up with some awkward situations where you've got a bunch of containers in the background that are taking up space. We don't want that. So just to be clean about this, we're going to always include that option. And then also, we're going to want to be able to actually have an interactive session with this container. We're going to want to be able to type commands in it. And to do that, we want to add in the -it option. And finally, we need to provide the name of the image, which of course is my image. So let's try running that. And you can see something has changed about my command prompt. So before it was my name and then the name of the computer I'm running on. And now it says root. So apparently my name is now root. I am the root user and then it's this random hash. So what's happening here is when you start a container, an instance of an image, it's going to give that container an ID, and that's this hash that we're looking at here. We can use this hash to refer to this particular container. And in practice, this is almost like having a totally different computer that happens to be running on the same hardware as the rest of my machine. We can think of this environment that we're running on as if we've logged into some remote computer. Again, it just happens to be running on the same hardware. If I type ls like I did before, and this at this point this will work even if you're on Windows, because we're in an Ubuntu image. If I type ls, you can see this is totally different than what it showed me before. If I type get --version, it says get command not found, because again, I've basically, it's almost like I've logged on to a totally different system. I'm in a totally different environment that is isolated, and Git was not installed in this environment. So if I wanted to install it, I would have to do something like apt-get update followed by apt-get install. So in just a moment, once this is finished, I will be able to use apt, the typical package manager for Ubuntu, and I can say apt-get install Git, and that should install Git for me. Now, I want you to notice something. What this command does is it basically checks to see can it find Git, and it does. And it figures out what's going to happen when it installs Git, and then it asks me if I want to go ahead and actually install Git. And so at this point, I'm prompted to say yes or no, and I'm just going to say Y, enter, and now it actually installs Git for me. And now if I say get --version, now Git is actually installed within this container. And I can then mess around in this environment. I can make changes. I can create files. None of these things that I do are going to persist. If I exit out of the container, which I can do by typing exit, okay, now I'm back on my local machine. I can type ls, and I could launch a container again. So I could go back and I could execute Podman RUN --rm -it my image. I can do that again, and now I can type git --version, and you can see git command not found, because when I installed git, I installed it in a container that happened to be launched from the image that I produced earlier. But once I exit out of that container, everything that I've done in that container, it's gone. It doesn't exist anymore. And as a result, I have no sense of persistent progress within containers. Now, if every single time I launch a container, I have to go back and reinstall all of the software dependencies that I need in order to do development work, that doesn't seem like a particularly good deal. And so what we're going to want to do is we're going to want to make changes to our image so that our image itself has all of the dependencies we need, things like git. So to do that, we can exit out of our terminal, and we can open our container file again, and we're going to make some edits to this container file that will have it install git. So I'm going to use the run command here. So this is a command that you'll be using very frequently when working with container files. And here, what I'm going to do is basically just write out the exact same commands you saw me do earlier when I installed git within the container. And so I'm going to say apt-get update. And then the way this run command works is it expects essentially a single command line, but we want to, it would be rather awkward to write everything on a single line. And so what we can do is we can say apt-get update &&, space / and what that's going to let us do is start a new command on a new line. So && would mean we want on a single command line to execute multiple commands, and then the / says we want to continue our run command in the Docker file. We want to continue that to the next line, and so I can just continue adding what's the next command that I want to execute. I want to say apt-get install, and as we saw, we executed install git. Well, there is one issue here, a minor issue, which is, if you recall, when we did this earlier, we were prompted to confirm that we did in fact want to install git. We were asked a question, do you want to proceed? And we had to type Y, enter. Well, this is going to be an automated script, and so there's not going to be anyone sitting there able to respond Y. So what we can do is we can add a -y option here, and that's just going to tell this apt-get install command, we want you to go ahead and proceed with the installation. Next up, we're going to have a line where we clean things up. So I'm going to say apt-get clean, and this is just a good idea to add this to the end of any run commands in which you're using apt, because apt-get update, that's going to pull in a bunch of data that, if you don't clean it up, is going to end up as part of your image, and it's just going to end up taking up space and make it harder to distribute to your colleagues and whatnot. So it's just a good idea to clean up any unnecessary files that you may have created. And so we'll do that. And then we're also going to clean our apt cache. So what we can do is rm-rf, and then the cache is going to be in /var/lib/apt/lists, and we want to delete everything there. So that's just sort of standard boilerplate. Don't worry if you're not too familiar with how apt works. Just know that these two lines are going to come most often at the end of any run command that involves apt. It's just a good way to do a little bit of housekeeping here. And so now we can exit out of that. We can open up a terminal, and we can say, once again, Podman build -g, and it's still going to be my image, period. And so we're just going to rebuild this. And you can see it's doing some things there. It's actually executing apt-get. And what we should be able to do now is Podman RUN --rm -it my image. And now you can see we're in this image. We can type git -- version. And look at that, Git is now installed in our image. And so we can add increasingly sophisticated dependencies just by modifying that container file and rebuilding. So at this point, what we could do is just add more and more to that container file to make sure that it's executing all of the commands it needs in order to install everything that we need to write our code, to compile it, and to run it. And that's quite powerful. Having said that, there's still an important piece of this container native development puzzle that we haven't worked out yet. One of the issues that we have right now is that anything we do in this container is purely temporary. As soon as we exit this container, any files we've created are going to be gone. So I could, for example, say touch test file. And that command is going to create a file if it doesn't already exist. So I can type ls, and you can see here is a file called test file. Well, if I then exit out of the container, there's nothing called test file anywhere anymore. It's just gone. It was part of the container. The container was purely this transitory thing. Anything created in it isn't available to us anymore. So what we can do in order to get around this limitation is we can mount a volume. So what we can do is say Podman RUN again. We're just going to change our run command a little bit. --rm -it, but then we're also going to have a -v option. And what this -v option is going to do is it's going to say, yes, normally a container is totally isolated from the host machine. Normally, none of the files that are available on the host machine are visible to the container and vice versa. But in this particular case, we're going to tell Podman we actually want the container and the host machine to share access to some particular directory. And that directory, I'm going to say, is going to be the same directory where I'm executing this command, the same directory where my container file is. And so I could specifically type out what that directory is. It's on my machine, it's /mount/data/podman. Or since this is Linux, a more general thing I could do is I could type $, and then in parentheses, pwd, print working directory. And that's just the command that says whatever my current directory is. And so that's just this right here is the same as if I were to specifically type out the full path to the directory where I am. And then after we've got, we list the directory on our host machine that we want to share with the container. Now we type colon, and we type what should be the path to this directory within the container. It doesn't have to be the same path. And so, for example, let's say that we want this directory /mount/data/podman to be visible within the container in a directory called /work. And so we've added that option in, then we just say my image. And if we execute that, okay, we're in a container now. We can type ls. And what you will notice is there is now a directory called work. It wasn't there before. We can type cd work, and now we are in this work directory. Now I'm going to type ls, and something kind of amazing happens. There's our container file. So we can actually see the file that was on our host machine. I can type cat container file, and it's going to list the container file. I can modify this container file at this point. I can say touch test file. I type ls. Now there's my test file. Okay, now let me type exit. I'm now on my host machine. I type ls, and there's my test file. So I just made a change in the container that persisted even after I exited the container. So now we've got all the pieces in place for us to be able to do container native development. We can write a container file that has all the instructions necessary to install all of our dependencies, all the tools we want in order to be able to develop all our library dependencies. And then we can launch that container with this -v option so that we're sharing some directory between the container and our host machine. We do our code development within that shared directory. We write code, we test it, we do whatever it is we need to do in that directory. And then when we exit the container, it's all still there. It's all still accessible on our host machine. We haven't lost anything. And so now we've got the ability to work in what is essentially a completely isolated environment from the rest of our system. And now, if we want to share that environment with our colleague, all we really need to do is share that container file or share the image that we've built. And then they can be working within exactly the same environment as well. So suddenly this problem, if it works on my machine, that largely goes away. And if we upgrade to a new computer, we just need to bring our container file along with us. If we have a different project that has different dependencies, well, we can just create a different container file for that project. And we use that as a different development environment for a different project. We can custom make our environments for whatever project it is we happen to be working on at any given moment. This is the power of container native development, and this is why container native development really forms the backbone of a lot of the best practices we're going to talk about in the rest of this series. Well, thanks for watching. Now would be a great time to like and subscribe, and if you want to see more resources like this from the MolSSI, you can go ahead and follow the link in the description below.